Thank you very much for the introduction. Thank you very much for the invitation. So yeah, the topic will be quite different from the previous talk. I will simply tell you about a bit of a different approach to the geometrical optics in relativity. Let me begin with a short outline. So first I will tell you the motivation why we did this research and tell you more or less what this biological approach really is and why it is useful. It turns out it can be formulated in two equivalent ways. You can try to go together via the geodesic deviation equation of the first order, or you can use the Singh's world function, which I will also define because it's not a standard topic in GR. And then I will tell you a little bit about the possible applications of this approach. So first of all, it is possible, with this approach, it's possible to notice and prove certain exact relations between optical observables in GR, which are not completely obvious. An example of these relations is the well-known Etherington's duality relation between distances. If you have the angular diameter distance and the luminosity distance to the same object and the redshift, there is a formula which connects them independently of the metric tensor. There is more relations of this kind, which you can easily discover if you have this whole mathematical framework in hand. And then you can also study with this framework relations between other types of distance measures. It provides a very natural setting for things like that. Okay, so a few words about this approach. So assume you've got a source of, so we are working completely in geometrical optics approximation. I will not talk about any wave effects. We've got a source, which is a particle moving along a world line in whatever spacetime we have. We have the observer's world line over here. I assume that there is at least one null geodesics which connects them. This is not an obvious assumption in relativity, as you might know. I assume that I know the momentary for velocity and momentarily for accelerations of both of them at the moment of emission and observation, respectively. And out of that, it's easy to construct what I would call the momentary observables, which is the position on the sky of the source as recorded by the observer in this particular moment, a kind of transverse vector orthogonal to the for velocity here. You can define the redshift as the ratio of frequencies of waves or an energy of photons emitted and observed. You can also define the viewing direction or the direction from which this thing is observed. If the emission is anisotropic, what the observer sees depends very much on this viewing direction, which is a vector in the emitters in the point of the emission, orthogonal to the for velocity of the emitter. But out of these primary observables, you can create what I would call the variational observables, which are related to the variations of these quantities when you displace the observation or the emission points. So this is, for example, the trigonometric parallax. If you displace the observer by a little bit, the position on the sky will change a little bit. There's also the angular size. If this body has a finite angular size, then again, there will be strictly speaking, a couple of positions of the sky or a whole angle, stereographic angle related to the angular size of this body. You have the magnification. You've got the drifts or the temporal derivatives of the position of the sky, so a proper motion type of thing. You've got the angular diameter distance, which you can also calculate if you know the angular size of your body, and if you measure the angular size of your body and you know its physical size. You've got the luminosity distance and many others I will not mention here. They're all related to the variations of these guys with respect to the positions of the emission and observation point. Now the idea is to express all of these observables as a function of, first of all, the kinematical variables, so the for velocity of the observer, possibly also acceleration, the for velocity of the source, and also it's possibly its acceleration. Obviously, this type of special relativity effect connected with the way these two guys move through the space-time also matter, so they have to be taken into account. But also we need an object which basically encodes the way wave propagate through a kind of narrow tube around our fixed null geodesic. And this will be a bilocal object, so object related to 2 points. It turns out that you can express it as a functional of the curvature along the line of sight. And this way you can encode any observable of this kind. I will show you why, how. So the advantage of this type of approach is that you have a unified view of many types of measurements you can make, including time measurements or drifts or variations. In fact, this was my original motivation. I wanted to have an exact expression for the drift of position and redshift in a completely general physical situation. But you can, another nice thing is that you cleanly separate the dependence on the spacetime geometry via the curvature tensor along the line of sight and the dependence on kinematics. But what we also discovered is that this object encoding the space-time geometry influence on these observations has a rich algebraic structure, which leads to certain exact relations between observables, which I think weren't always known before. Some of them were, but some of them I think were not. Yeah, so you have relations between parallax, angular size, redshift transverse variation, position drift, and so on and so on. I will talk about them a bit later. And also, this is a natural setting to ask questions like, what can we learn about the spacetime by comparing, for example, the parallax distance and angular diameter distance to a single object at a given moment? They don't have to be equal. The whole talk is based on a couple of papers, but the main one is the first one here, the one written with Nazihe Uzun, algebraic symmetries of the observables on the sky, variable emitters and observers. So let me begin with the geodesic deviation equation approach to the bilocal approach. So we start from the following situation. We've got a null geodesic. It's parameterized backwards in time just for convenience. L denotes the tangent vector. O is the observation point, E is the emission point. We can write down the first order linear geodesic deviation equation in this form with the curvature tensor. It's very easy to massage it into a first order equation. This is a second order equation, and I would like it to be a first order equation. The trick is simply to take psi and the derivative of psi as independent variables, and then you end up with this type of equation for a larger object vector of 8 components. Okay, but a first order linear ODE of this kind can be always solved with the resolvent method. So you can express the state of affairs at let's say point lambda 2 as a function of the state of the system at point lambda 1 and a linear mapping W from lambda 1 to lambda 2 over here. And this is known as the resolvent. In this setting, it's an 8 by 8 matrix, which has a natural block matrix decomposition into 4 by 4 matrices. By the way, if you are familiar with the Jacobi propagators, formalism, and their derivatives, they were known since 1970s, and basically W is a matrix composed of these objects and their derivatives appropriately over here. So in a sense, this is not something terribly new, but looking at this object from a global perspective, I think is quite new. Okay, we can also fix a frame for vectors, a time-like vector, some kind of for velocity, to transverse vectors E1, E2. And usually people take another third spatial vector, but I prefer to take L as my fourth vector. I can parallel propagate this basis, and in this basis, you can write independently an equation for W, a first order ODE for the matrix W, in terms of the basically Riemann tensor along the line of sight. And with this type of initial data, we've got our W for n times. And it's obvious that W is a functional of the curvature along the line of sight. Mathematically speaking, it's a mapping from the direct sum of the tangent space at, let's say, observation point O and the cotangent space at point O to the direct sum of tangent and cotangent space at point E. Direct sum is basically a more clever mathematical way of talking about stacking 4 by 4 vectors, one on the other. Okay, that's interesting, but what's more interesting is that this object has a couple of algebraic properties, which are quite interesting. Some of them are fairly easy to guess. Since it's a resolvent of an linear ODE, it needs to have the property of composition. If you go from the point lambda O to lambda 2, you can stop at an intermediate point lambda 1 and write W from lambda O to lambda 2 as a product of W from lambda O to lambda 1 and lambda 1 to lambda 2. It's kind of obvious. On top of that, going back involves simply inverting this matrix. W from point lambda to itself is always a unit operator. What is less obvious is what happens when you plug in this vector L, the tangent vector to my null geodesic W. It turns out that the result is independent of the geometry. If you plug it in this upper part, you get L at the emission point simply. If you plug it in the lower part of this big vector, what you get is again proportional to LE. But here there's a proportionality constant, which is basically the affine distance along this null geodesic delta lambda between the points O and E. And there is a complementary set of almost identical relations, which you get when you multiply it with the covector on the left-hand side. They look surprisingly similar. Yes?
Slide. Yes. What are the assumptions you make on Riemann?
No.
Can Riemann be function of time?
Riemann is, I don't make any assumption about the space-time metric. Riemann can be, it's going to be a function of the affine parameter along the line of sight, and can be anything.
Also a function of time?
Yes. Okay. It's a completely general framework for everything. There's no, I make no assumptions about the space-time whatsoever. It's pure geometry for what I'm doing here. Okay, so these properties are kind of built into this formalism, but there's another important property, namely, if you take this matrix J, it turns out that it is preserved by this W over here. This J is a symplectic matrix, so W preserves a symplectic structure in this space over here. This is not a surprise, because as Nezika noticed last time, the geodesic deviation of the first order is a Hamiltonian system. If it's a Hamiltonian system, it preserves a symplectic structure. And basically, if you look at this thing from the point of view of Hamiltonian system, these are conjugate variables, the positions and the momenta. So unsurprisingly, the dynamics, linear dynamics of this system preserves this symplectic structure. From my point of view, it's just a property of the matrix W, which has to hold, but a non-trivial property. And one more thing, you can also show that if this set of properties holds and the matrix is symplectic, this set of properties also needs to hold, and vice versa. So these properties are kind of dual to each other under this symplecticity relation. Another important algebraic property is that there is an invariant subsystem hidden in this system, namely the transverse subspace. So you can, in this framework, you can limit yourself just to solutions which have components in the direction of E1 and E2, which are orthogonal to the vector L. If you choose the initial data appropriately, this is preserved all the way along the null geodesic. So you can basically limit yourself to studying just the transverse subspace of the full tangent space. And that's pretty much what almost every geometrical optics textbook does usually. So there's, in this big 8x8 matrix, there's a 4x4 submatrix composed of 2x2 submatrices, which is decoupled, whose dynamics is in a sense decoupled from the rest. It also has its own reduced symplectic form, and it is symplectic with respect to this reduced symplectic form, and was used also by many authors. Yesterday, Nezika used it in the form of the ABCD decomposition, but I don't call it this way. It was also used by Pierre Fleury in his PhD thesis. Okay, this is from the physical perspective, this is an important subspace, namely exactly because it describes momentary measurements. So if you limit yourselves to perturbations of geodesics of this kind, you're looking at perturbations which lie on the same wavefront. So they describe light emitted at a given particular moment by the source, or light observed by the observer at a particular given fixed moment. So a lot of observables can be recovered just from this submatrix, as you will see later. But this is not the whole story. As you notice, there's also two additional components which are of interest. By the way, these two guys, WXX and WXL, are also important in the sense that they govern the infinitesimal bundles of rays. In particular, WXL governs the behavior of the bundle of rays, which has a vertex at O. So you imagine an infinitesimal bundle of rays, a kind of small congruence which has a vertex at O, emanates from O, and goes basically along this null geodesic. Its properties are exactly given by WXL. If you fix a vector over here, you have the property of particular geodesic along the line over here. WXX, on the other hand, governs geodesics which are initially parallel to this first one. And this thing over here is also known as the optical Jacobi matrix. So if you are familiar with the Jacobi matrix from geometrical optics, it sits over here as a submatrix of this whole big W thing. Okay, but from the point of view of calculating the observables, this is not the best you can do. W corresponds basically to solving the initial value problem. You give the initial perturbations, for example, at the observer's side, the initial displacement of a geodesic, plus the initial variation of the tangent vector, and you get to the displacement and the variation of the tangent vector at E. From the point of view of calculating the observables, what is more interesting is the boundary value problem, when you specify the variation at the observation point and at the emission point. Fortunately, this is a linear relation, and it's fairly easy to move between the initial and boundary value formulation. In particular, you can solve this, you can massage this equation here into the following form. You can express the variations of L at the two endpoints by the variations of the positions of these endpoints over here. I'm using a minus sign because it turns out that it simplifies a lot if you take a minus sign over here. I will call this thing here U. It's obviously related to W, and I will show you in a second how. U is a kind of complementary way to encode the properties of space-time and how it conducts waves, how null geodesics behave between these 2 points. It's an object between the simple sum of the tangent space at O with the tangent space at E, and maps it to the simple sum of the cotangent space at O plus the cotangent space at E. But there's another way to look at that in which this U becomes something simpler. Instead of thinking in terms of the space-time itself, we discovered that it's pretty nice to think about the terms of the product of the space-time by itself. So kind of a Cartesian product of M by itself. So the space of pairs of points from the space-time itself. It also has a metric. You can give it a geometrical structure. It's an 8-dimensional manifold. And it turns out that in this case, U is just a tensor here. It maps vectors from the pair of points OE to covectors OE. So it's a basically rank 2 tensor in this thing, in this extended space-time M times M. Okay, what is the relation between U and W? Well, actually, you need to calculate this type of block matrix operation you see over here. You can also calculate the relation between W and U. And if you do it, you might notice something very interesting, namely this picture and this picture is actually the same picture. What does it mean? Well, it means that you can look at this formula over here as defining an operation on matrices, more precisely matrices for which this 4x4 submatrix is invertible. And what happens is that the resulting matrix U is also invertible in this sense. You can reapply the same operation and you come back to the same matrix. So this is, we have defined an analog of taking an inverse of taking a transpose of a matrix, a kind of involution. If you apply it twice, you always come back to the same matrix. And now switching between the initial value problem and the boundary value problem is simply applying this operation one by one. What is also interesting is that this operation, if you do your calculations correctly, maps symplectic matrices W to symmetric matrices U, and vice versa. And that's very important because this allows us to consider the symplectic property of W in a bit simpler algebraic form as the property of U being symmetric. Okay, alternatively, you can also approach this problem via the sinks world function. If you're not familiar with that, sinks world function is a function of pairs of points on a manifold, and it's basically given by the integral of the gamma dot, where gamma dot corresponds to the geodesic linking these two points over here. So it's a function of pairs of points defined using geodesics. The funny thing about it is that its first derivative corresponds basically to the tangent vector to the single geodesic passing from the point x to x prime. And vice versa, if you take the derivative with respect to the other point, you get the tangent vector, which takes you from x prime to x. So in a sense, it solves the boundary value problem for you. If you have a complicated metric, you don't know where to shoot your geodesic in order to reach a particular point. If you know the world function, it's fairly easy. You just calculate the derivative of the world function and you know how to do it. On top of that, you can also use it to check whether the pair of points can be linked by a space like null or time like geodesic. So it's a useful object, which Singh used quite a lot in his textbook, and then it's also used in other fields. Now it's very closely related to U, namely the matrix U is nothing else but the Hessian of sigma of the world function, the matrix of the second derivatives with respect to all possible arguments. So if you make an expansion of sigma in the vicinity of a pair of points, you get basically the tangent vectors L over here plus U. So the matrix U can be considered simply a Hessian of the sinks world function. By the way, the relation between Jacobi propagators and these derivatives was known since 1970s. I'm not claiming this is very new, but this approach and this global approach and application to the geometrical optics, I think, quite new. Okay, if we want to go to observables, there's one more important point I have to make, namely, we're not allowed to take any variations of the endpoints we want. We have to preserve the null character of the connecting geodesics, and that's a non-trivial condition. We have to make sure that the, for example, initial variation of L times L is equal to 0. Fortunately, it's easy to translate this condition to this boundary value problem language. You just have to make sure that the variation of X times the tangent vector at O and the variation at E plus the tangent vector at E, that these products have to be equal. If this is satisfied, then the perturbed geodesic will also be null. This is automatically satisfied if you have just transverse perturbations in the sense of O and E being perturbed in transverse directions. But if you are also interested in time variations, this is not a trivial condition. So assume that you want to calculate a derivative with respect to the observer's proper time of any of these primary observables. You have to make sure that the variation of this point over here is basically proportional to UO. And the variation of this point over here is proportional to UE, but there must be a proper proportionality constant to make this thing correct. It turns out that this proportionality, that this prefactor over here has to be 1 over 1 plus the redshift, which physically makes sense. It simply encodes the fact that UO observes all the flow of time at the emitter's frame slowed down by the redshift factor. So redshift, on the one hand, governs the energy, the difference of measured energy of a photon, but it's also a slowdown factor. O observes everything happening slowed down by the factor of 1 over 1 plus z, and we take this into account when we slide simultaneously the endpoints of the geodesic on both world lines. Okay, so now we can take the redshift or the logarithm of the redshift, and we can try to calculate the derivative of this quantity as the observer's time passes by, and we take basically the variation with respect to this vector t. The variation of the tangent vectors LE and LO is something we can express using this matrix U and this vector t. The variations of the tangent vector of the for velocities UE and UO, they're expressible in terms of accelerations, obviously. So in the end, we get a fairly neat formula. This is equal to this matrix U times TT. Use this thing over here. And here we have a Doppler effect. Basically, these two terms pick up the radial part of acceleration. So there's a an obvious special relativity Doppler type of effect of accelerations of these two guys over here. But on top of that, we have all GR effects encoded in this thing here. The same way you can, for example, calculate the magnification matrix, which basically tells you how physical sizes of objects at the emission point translate to the two angles on the observer's sky. It's related to UOE. You can calculate the parallax matrix, which tells you how the image of a source is displaced when you displace the observation point a little bit and perform the measurement in the same with the same for velocity and with the same in the same moment. It's proportional to UOO. 5 minutes, okay? And you can calculate position drift, viewing direction drift, and so on. Now, exactly because U is symmetrical, you'll have relations between various observables. In particular, you'll have a relation between, in particular, the fact that UOE and UEO are transpose of each other. There's a reciprocity relation between the Jacobi matrix and the Jacobi matrix calculated from the emission point. And this results in the well-known Etherington's reciprocity relation between the luminosity distance and the angular diameter distance and the redshift. This part was known, but there are also other interesting consequences. One of them is the relation between the transverse variations of the redshift and the position drift, and the fact that the parallax matrix is symmetric. I will tell you more about those. We managed to list in our publications, I think, all possible consequences of this algebraic fact. So now imagine that you have a source with some kind, which emits some kind of monochromatic light. You measure its frequency at some point O, but you also have two displaced observers, which are co-moving with this one. They're displaced in two orthogonal directions, and they measure slightly different omega. This defines some kind of transverse variations of the redshift here. It turns out that this transverse variation of the redshift is directly related to the position drift, or proper motion as observed by the observer of this thing over here. And for a non-accelerating observer, for an accelerating observer, you also need to subtract the aberration drift, so the effect of aberration, simply because this guy is accelerating. But for a geodesic one, there's an exact relation between the total position drift or proper motion on the sky and this, what we call parallax of the redshift. We did not expect this to happen. In special relativity, it's something that is very easy to prove without all of this machinery. You can do it in your, if you are teaching special relativity to undergraduate students, that's something you can verify yourself during the exercise. It's very simple, but it turns out that this works absolutely well in a more general situation in every spacetime. There is also the fact that the parallax matrix is symmetric. So if you combine the position of a single object as registered by 3 observers, the yellow one, which is the central one, and 2 displaced ones, they will not be exactly on the same point. However, no matter what happens, you can see that 2 of the components of these displacements have to be equal, provided that these displacements here are equal. This is the result of this thing over here being true. By the way, there is no corresponding relation of this kind for the Jacobi matrix or the magnification matrix, which is a kind of dual object related to what happens when you displace the emission point. So it's well known in lensing theory that the magnification matrix does not have to have any special properties. It can be as complicated as possible. Okay, I have 2 minutes, so let me just talk about distance measures in relativity. It will take 2 or 3 minutes. So you can measure the distance in relativity using the angular diameter distance by comparing the angular size of an object of this size with its transverse size. In a general spacetime, of course, the relation between displacement and the angle is more complicated, but we can take the determinant of m to be to define our angular diameter distance. This is the standard definition. It depends on the geometry along the line of sight and the velocity of the source. Yeah, and you can express it using WXL or the Jacobi matrix, basically. You can also do the same with the parallax distance. So in a general spacetime, parallax, geometrical parallax effect is a bit more complicated than the usual one. It's given by a matrix which relates the displacement of the observer with the displacements of the image of a source. The parallax matrix can be written down this way. You can prove it fairly easily. This first thing here is actually the magnification matrix, and it's multiplied by this WXX. You can calculate the parallax distance, again taking the determinant of this whole thing over here. In a flat spacetime, it's identical to the angular diameter distance between these two objects. And it also depends on the velocity of the observer because of the aberration effect. Now, you can do a simple thing. You can try, for a given object, you can calculate the ratio of the determinant of the parallax matrix to the magnification matrix, and take 1 minus this thing here. Obviously, in a flat spacetime, these two matrices are both proportional to 1 and, in fact, equal, so this is equal to 0. It can be expressed using distance measures. So basically, this quantity is nothing else but the ratio of the angular diameter distance to the parallax distance as measured between some kind of observer and some kind of source at a given moment. Strictly speaking, there is a sign prefactor over here for which flips the sign for inverted images, but let's forget about this for a second. For simple images, it's just the relative difference between the angular diameter distance and the parallax distance. You can also express it using luminosity distance, like that. Now, the funny thing about this quantity is that it vanishes in a flat spacetime. And secondly, it's always frames independent. So it has no dependence on the velocity of the observer or the emitter, even though all these quantities here very much depend on the velocities of these two guys over here. But this quantity is, in fact, Lorentz invariant in both endpoints. For short distances, it's given basically by the integral of the stress energy tensor along the line of sight with a kernel. Okay, so tiny difference between angular diameter distance and parallax distance between some source and some observer measures somehow the matter content in the along the line of sight. We also managed to prove a bit more general result. We managed to basically show that if the null energy condition holds, then under certain assumptions, the parallax distance has to be larger than the angular diameter distance. This is a stronger, more non-perturbative result from this paper over here. So basically, we proved that if the null energy condition holds, and there's a technical requirement, the bundle of rays, which is parallel to O at O, has no singular points between O and E. So there is no recollapse to a line or to a point. Then the parallax distance has to be larger or not smaller than angular diameter distance, and these guys can only be equal if there is no Ricci focusing or Weil focusing either. In short, if null energy condition holds, then parallax distance has to be larger than angular diameter distance up to the first singular point coming from O. So there is the relation between these two distance measures has a concrete sign. Okay, so that's pretty much the end. So I reached the summary. So I presented the bilocal approach to geometric optics, which is a bit of a unified approach to many different types of observables you can find. It includes the time variations of drifts of redshift, position, as well as positional variations, so parallax, variations of the viewing angle. I haven't talked about those, and magnifications in a consistent way. The algebraic properties of W, the object encoding the way light propagates between 2 points. Basically, they imply certain general relations between observables, which some of them were known, others not so much. I also managed to prove a few results regarding the relationship between the distance measurements. The parallax distance is different from the angular diameter distance and the luminosity distance, and the relative difference carries information about the matter density along the line of sight, and the sign of this distance tip here is directly related to the null energy condition under fairly mild conditions. Okay, thank you very much.